We know that as we add more layers to the surface area of the sphere, it gets added to the total volume. So, by increasing surface area, we increase volume as well. Therefore, we can deduce that the rate of change of the volume of the sphere is equal to the surface area of the sphere. Since we know conceptually that the derivative is just rate of change, we can deduce that by differentiating the volume, we get the surface area. But can we prove it algebraically? Consider a small increase in the radius of the sphere, represented by the black layer, which we will call dr, and dv will be the change in volume. Now, if we squish the outer shell of the sphere, we can denote that the height of the squashed sphere is 2dr. Since the sphere will be circumpressed, it will only consist of two circles on top of each other. Hence, the top circle is dr and the bottom circle is also dr. Thus, top circle plus bottom circle equals dr. But what is the area of the base? The area of the base of the flattened sphere is 4 pi r squared over 2. But why is it over 2?
Thanks, Alex. I'll take it from here. We know it is over 2 as the picture clearly demonstrates the process of the sphere slowly becoming compressed to the point where the top half and bottom half of the sphere become two singular spheres. Ultimately, this leads to the conclusion that the surface area is therefore half and their squash circle is now 4 pi r squared over 2. From this, we are now able to find the volume using the following formula. Volume is equal to base times height. Now, from subbing in, volume is equal to 2 pi r squared times 2 dr. From here, we understand that dv is the change in volume and is represented as dv equals 4 pi r squared times dr. Furthermore, if we divide both sides by dr, we get dv over dr, which is equal to 4 pi r squared. Therefore, we arrive at the conclusion that the volume of a sphere is equal to the surface area of a sphere. In a similar way, the derivative of the area of a circle is equal to the circumference. This can be easily demonstrated in the following diagram. The change in area, or the derivative, will be represented as dA. dA is equal to 2 pi r times dr. Therefore, dA over dr is equal to 2 pi r. Therefore, it is clear that there is enough proof to show that the derivative of the volume of a sphere is equivalent to the surface area of a sphere.
As with formulating any proof, it is essential to prove that our spherical equations are applicable in all cases. Since these are related to the field of geometry, it is important to ensure that they are true for all theoretically possible spheres. This can be proved through an understanding of first-order calculus. Since we have already determined the derivation relationship between spherical surface area and volume, it can be said that any increase in radius will increase volume proportionally. Determining the proportion can be represented graphically. Graphically, it is important to remember that the shape of the surface area line is representative of the rate of change we see in our volume graph. Moreover, it can be inferred that for all potential values of radius in any given theoretical sphere, it can be said that the volume equation is true, and subsequently, its derived surface equation is also valid, as it graphically can be seen to represent the rate of change in volume. Hence, it can be said that all real spheres can have their volume and surface area determined by the respective equations of volume equaling 4 on 3 pi times the radius to the power of 3, and surface area being equal to 4 times pi times the radius to the power of 2.
When the dimension of a unit radius sphere in high dimensions increases, the volume of a sphere decreases, approaching 0. Similarly, as the dimension n increases, the surface area reaches a maximum but then decreases towards 0. However, despite this nature, the relation of the surface area of a sphere stays true even in n dimension. The surface area of an n-dimensional sphere is related to the volume by the differential equation as seen on the screen, and the completed derivation of the recurrences. From this, below are the equations for the volume and surface area of a sphere in n dimension, closed form after combining the recurrences. The volume of a sphere in n dimension and the surface area of the sphere in n dimension. Where gamma function is involved, r is the fixed radius and n is the dimensional number. For example, n equals 9 is the 9th dimension. Since the volume is proportional to the power of the radius, the relation formulates the equations of the surface area of a n-dimensional sphere and the volume of a n plus 1 sphere, or volume of a n sphere and the surface area of a n minus 1 sphere. This is similar to differentiating a sphere in third dimension, where volume equals 4 over 3 pi r cubed differentiates into surface area 4 pi r squared, where the power of the radius is the surface area equation, where the power of the radius in the surface area equation is n minus 1. The recurrence can be seen in lower dimensions, such as in the 0 dimension, the volume equals 1, surface area equals 2. In the first dimension, volume equals 2r, surface area equals 2. In second dimension, volume equals pi r squared, surface area equals 2 pi r, and so forth. Therefore, the volume and surface area of a sphere, along with the volume and surface area in the 0 dimension, are related to the recurrence, and thus the relation does in fact hold in higher dimensions.
Okay, is that the end?
Yep, that's all.
Okay, that's not all, Alex. That was awesome. That was great. Thank you. Well done. This is so cool. I'm very impressed. All right, has anybody got any thoughts or questions of Alex and his group? Awesome work. Okay. People aren't giving things up easily today, are they? All right. So, Abby, you've requested to go next, so take it away. It's all yours. Thank you.
Can I go next? I'm here. Can you go next?
Abby wants to go next and has asked for that, so I'll let Abby go and then you can go. You're not in the same group, are you? Yeah.
No problem.
Okay, give me 1 second. I'll just. Okay, so my group also looked into the surface area, volume, and volume of the sphere. People in my group is myself, Abby, Anthony, Nicholas, and Kevin. So we just wanted to make, where is it? We just wanted to start by making a really quick disclaimer, as I'm sure most of you have realized now that the topic you have presented, as well as ours, there's not a lot of information on it. We will simply presenting what we do know, as well as some of our theories as to why the surface area of a sphere is the derivative of its volume. And to do this, we will start by explaining the origins of the two formulas, as well as their relationship. And we'll also be looking into the idea of higher dimensions and other areas where we can see this relationship. So first I'll be discussing who proved and discovered the surface area and volume of the sphere. So Archimedes was one of the first mathematicians to derive and fully explain the formula of the volume and surface area of the sphere. He used a method called the heuristic method, which was presented by Imre Lakatos in the 20th century. The heuristic style is essentially showcases practical methods to emphasize definitions created by tests to approach a solution. In other words, Archimedes conducted physical experiments which led to the geometric discovery of these two formulas. Now, I don't know about you guys, but if someone asked me to look at a ball and determine its volume, I probably wouldn't know where to start. But in the case of Archimedes, he started with the volume of a cylinder and the volume of a cone. He was able to determine that if the radius and height of a cylinder were double the length of its corresponding sphere, and the sphere would be half the volume of the cylinder. Similarly, if the radius and the height of the cylinder were equal to that of the cones, the cone would also be half the volume of the cylinder. So once he figured this out, he already knew the volume of the cone and the cylinder, and because he knew that and its ratio, he was able to derive the volume of the sphere from those, as we can see on the screen. And then for the surface area of the sphere, Archimedes created an analogy where the circle is equal to the area of a triangle, where its height is equal to the radius of a
Talib,
circle.
I'm happy for them
By
to play
using
the
the volume of
video
the sphere, he
as
concluded
their
that the surface
presentation.
area of the sphere is 4 times
I'm
the
happy for them
area
to
of
play
its
their video as
orthodrome,
their
which
presentation.
is the intersection of the sphere with the plane containing the center of the sphere. And basically, from that, we can
So I'm
go
happy
into
for
a
him
better
to do what he
understanding
was doing.
of the
He can just
relationship between
continue
these two
presenting.
formulas.
So he can take the share of the screen and play his presentation the way he was. That's fine.
Oops.
Thank you.
So when we explore the derivatives of the volume of the sphere, we have to go back to the basics. So during high school, at some point, we have learnt the formulas of the volume of the
just go back
and
to what
surface
you were
area of the
doing.
sphere. So the volume is 4/3 pi r cubed, and the surface area is equal to 4 pi r squared. If we get the derivative of the volume using the power rule, we can see right away that it would be equivalent to the surface area, but that doesn't help us see a relationship. So we know the derivative of the volume is dV over dr, but what do they represent? Well, dr represents the change in the radius and can also be visualized as a layer of paint covering the entire surface area of a sphere. The dV represents the change in the volume, which surprisingly is found by the area times dr. And since we know the area of the sphere, we can determine dV equals 4 pi r squared times dr. At this point, we have to take dV, the rate of change of the volume with respect to the radius, to return the surface area formula. It is clear that there is a relationship between the rate of change of both the volume and the radius of the sphere, but the question now is, does it hold in higher dimensions?
When looking at the relationship between surface area and volume, a commonly asked question is whether or not the simple relationship we are all aware of between volume and surface area of 3D objects actually applies in higher dimensional states, and if there's any particular formula or pattern for determining it in these situations. Firstly, based on the research that my group has done, as you can see, the relationship between surface area and volume for a sphere remains constant as you increase the dimensions. Look at the first image in the presentation, and it shows what the volume and surface area are between the 3rd and the 6th dimension. And you can clearly see that if you differentiate volume in all of these instances, you end up getting the surface area for that particular dimension. The question we now need to ask is, well, how is this known? Ultimately, in order to work out the surface area and volume for higher dimensions, the concept of a Euclidean ball needs to be required. And in short terms, a Euclidean ball, it's basically like a regular spherical object, but it can have any number of dimensions, and ultimately this was needed so that they didn't have to constantly just keep doing guesswork for these sorts of situations. They needed some way of knowing, and instead of creating new formulas for every single dimension. And as you can see with the volume and surface area formulas, one of the key components is the Euler's gamma function, which basically, what that function involves is it's like an n. It's basically it substitutes in an n-1 factorial into any situation, which then allows the volume and surface area to be calculated. The surface area and volume of the Euclidean ball, as you can see, have a clear relation with each other. And if you were to differentiate with respect to r with the volume n ball, you would get the surface area for the volume n ball, thus showing that regardless of how many dimensions the sphere may have, the standard derivation for volume, a surface area, still holds. Go on to the next slide.
The main real-world application is being able to calculate the surface area of spherical objects through deriving a known volume or using integration for the opposite effect. However, this derivative relation can be useful when applied to other areas such as in physics with motion. Instead of a shape, a vector known as displacement, whose length is equal to the minimum distance from a starting point and ending point, is connected to velocity, which refers to the rate an object changes position. As shown in the formulas, if we let displacement equal s, then velocity is equal to ds over dt. Knowing this can be useful in calculating the velocity of an object given its displacement. Next slide. Furthermore, the higher derivatives can also provide use, as the derivatives of velocity gives acceleration, which is the rate of change in object's velocity. This is seen as the formula's double derivative. This continues many steps down, as shown in the table with jerk, snap, crack, popple, lock, and drop. Spherical objects aren't very common, so another real-world application would be knowing if the surface area to volume relation holds true for other shapes. In the case of cubes, if the variables chosen are analogous to a sphere, you can show a similar result. This is done by using a radius like sphere instead of a diameter, so a side turns into 2r. This results in volume's formula of a cube changing into 8r cubed, and the surface area of a cube changing to 24r squared. As the surface area now matches the derivative of volume, it shows this concept closely applies to the cube. Overall, through visualizing a sphere's volume with cylinders and changing radius, the corresponding calculations made it clear how the volume of a sphere, when derived with respect to r, will give the surface area of a sphere. In addition, understanding how the relation stays true for an n ball supports that this relation of volume and surface area holds in higher dimensions. Then this relation significance is shown through real-world applications within motion and how it can apply to cubes as well. All of this answers the investigation into the special relation between the derivative of volume being surface area and how it applies to other dimensions and shapes.
Okay. Okay, well done. Just managing all the stuff that you guys are doing. It's awesome. Has anybody got any comments they would like to make or ask any questions? Okay, so some great feedback there. Okay. All right, so Queen, you've asked to go next, and that means that Hannah and I've asked you to wait until Queen's group is finished. So, if you could go ahead, please.
Yeah, okay.
Thank you.